So in this problem, we have a wave that is moving at 343 meters a second. We are asked to find the wavelength if the resulting frequencies of those said waves is 20 hertz, 20,000 hertz, and 28 megahertz. So how do we go about a problem like this? Well, it's actually quite simple. We know that, and I'll draw my annotations in blue so you don't miss them. The velocity of a wave, or wave speed, let me make sure, yeah, you can see that, is equal to, it's going to be lambda, which is the wavelength which we're trying to find, times frequency. So to find lambda, we just divide by frequency, so velocity over frequency, and that will give us wavelength. If you don't believe me, notice how the units of velocity is meters a second, where we're dividing by a frequency of a second. Alrighty? Or sorry, frequency is to the -1 as well. So these reciprocal seconds will cancel and you'll just get meters. That's what we're trying to find here, is that how long is the wave itself? How can we mathematically show that? So all we have to do is know that a hertz is a reciprocal second, and we'll convert megahertz to hertz when we get to it, but let's do the 20 hertz question now. So we can imagine that this wavelength is going to be quite long, okay? Why do I say this? Well, notice the relationship. If lambda equals the 343 meters a second, right, that's given to us here. The wavelength of speed at 25 degrees Celsius is 343 meters a second. We're dividing it by a relatively small number, 20 hertz. Compare that to this equation where we're going to say, okay, we're going to take that, but we're going to divide it by 20,000. So we expect the wavelength here to be a lot greater than the wavelength here, and that should make sense to you, because a 20 hertz means I'm doing 20 things per second. 200,000 hertz is saying I'm doing 20,000 things a second. I'm doing a wave 20,000 times a second. So you can imagine at 20 hertz it's looking like this. But 20,000, it's going like fucking crazy, man. Like that is a nasty little wave in comparison to a 20 hertz wave. So let's run the math here. Let me grab my calculator. 343 divided by 20. We're going to see that the wavelength is 17 meters. That's a big wave. All right, think about like a football field, like a fourth of a football field, that is, right there. So it's going like kind of long. Okay, now for this here, let's find what that's equal to. 343 divided by 20,000. We're going to see that our wavelength is 0.017 meters. Okay, so it does make sense with our theory. If it's 20,000 hertz, it's going really fast throughout each oscillation, right? And the resulting wavelength, assuming that it keeps a constant speed, that just means the wavelength is going to need to be shorter, right? So what this wave looks like, I'll draw the relative wave and what it looks like. So here's that wave. And they are longitudinal waves. We're going to put them as transversal waves. Remember, longitudinal is differing pressures in air molecules. That's how those waves travel. This wave is just traveling at more translational. This wave would be like this in comparison. So just like a lot closer of the troughs together, right? And again, they are longitudinal waves, not transversal waves. Okay, and then finally we have 28 megahertz. What is that in hertz? Well, it's 28 for every 1 hertz. There is, or sorry, this is not correct. Dimensional analysis. Why am I complicating this? Oh wait, that doesn't make much sense, does it? Oh, I see where I went wrong. 28 megahertz. Okay, for every 1 megahertz, we have 10 to the 6 hertz, right? Because a mega is a suffix for 1 million of something, right? So if I have a megagram, I have 1,000,000 grams of that thing, right? So we're just converting it over to hertz, and that just requires the multiplication, right? And you can see why they kept it as mega, because expressing it as the way we're about to express it is kind of stupid. 2.8, let me just make sure that you can see. 2.8 times 10 to the 7 hertz. Like, who expresses that in that way? Yeah, I have 2.8 times 10 to the negative 7 hertz coming out of my speaker. No, you have 28 megahertz coming out of your speaker. Hopefully that makes sense. So let's run our calculation. 343 meters a second over the 2.8 times 10 to the 7 reciprocal seconds. Well, that's going to give us 343 divided by 2.8 times 10 to the 7. Well, we found that our wavelength is 1.2 times 10 to the negative 5 meters. So notice, and I'll go ahead and try and draw that wave. Might not work very well. Okay, so let's kind of just review the question here. So if we have a 20 hertz wave and it's traveling at a constant speed of 343 meters, we know that that wavelength is going to be 17 meters, and the wave might look something like that if it was transversal instead of longitudinal waves. Here we are going to up the frequency, but keep the velocity of the wave constant. So we know from this equation, if our wave speed is constant and we increase frequency, well, lambda, which is wavelength, needs to go down. And that's exactly what we have here. The distance between the oscillations is a lot closer together. Here we bump the frequency even higher into the millions of hertz, specifically 28 million hertz. So again, we're really increasing the frequency. We really need to drop that wavelength. The distance between the troughs is so low here compared to here that if I was drawing comparatively, it's just like a line. It's like a barcode, if anything. So hope you guys enjoyed. If you did, please drop a like, subscribe, and comment if you have any questions. I hope you have a wonderful day.